Hi everyone, here we're going to explain the transverse wave section of the Waves, Optics and Acoustics course to you. Here are some useful definitions and their equations you should know. The partial derivative of the wave function with respect to time is the wave velocity, and with respect to its displacement along the wave is the rate of wave disturbance. Impedance, Z0, is a measure of the resistance to motion of the force driving the wave. The reflection coefficient represents the proportion of an incident wave's amplitude that is reflected backwards and is a function of the impedance of the media the wave is traveling in. Likewise, the transmission coefficient represents the proportion of an incident wave's amplitude that is transmitted and is also a function of the impedances of the media of which the wave is traveling in. Resonance is a phenomenon that occurs when a system oscillates with its greatest possible amplitude close to its natural frequency. 3.1. Let's start with driving and terminating a wave. With the exception of light, because light's weird, real systems, waves, for example, need to be driven. If a wave is to continuously propagate along a string, it requires a driving force. To do this, let us consider a string of length L with ends at x equals 0 and x equals L. The equation used is the traveling wave equation used earlier in section 2.4, for simplicity's sake. The driving force at any instant must be proportional to the transverse velocity of the wave. This is similar to the resistance or damping in a harmonic oscillator. This resistance stems from loss of energy to friction, air resistance, and the like. Hence, a constant supply of energy is required to keep a wave with constant energy going. Impedance, which in this case is a measure of said resistance, is only dependent on the system and not on the type of motion or frequency.
Imagine a wave propagating through a medium, such as a string, that is attached to a fixed wall at one end. Fixed objects, such as walls, have very high impedances, and so waves are reflected back, moving in the opposite direction. Doing this in mathematical terms, the displacement at x equals L, where the string is attached, should be 0. Equating this, we find that the reflected wave has the same amplitude, but in the opposite direction compared to an incident wave. This phenomenon can also be seen in the following video. Now, what happens when instead of a solid fixed wall, the string is now attached to another string with a different density, mass per unit length? Strings with different densities have different impedances. Now, if one string has a wave propagating through it, at the point where the two strings are attached, both of them should have the same wave functions. When we equate these wave functions, we can find the coefficient of reflection for the wave. This is a wave function in the second string, and this is a wave function in the first string. Notice that the differential with respect to time of the reflected wave has a negative sign because the direction of motion is opposite to the propagating wave. We also notice that to have a continuous wave in the string, we need some wave transmission to the second string. The coefficient of transmission is found out as shown, along with the possible values of both the reflection and transmission coefficient.
Standing waves. We will now be considering setups where both sides of the string are attached into their position, meaning each end of the string is a node. These waves will have the sinusoidal form shown. Because a standing wave by definition has these boundary conditions, the waves that fit inside these boundaries can only take certain wavelength values. These wavelengths in this case are calculated using the boundary conditions x equals 0 and x equals L. As we can see, for the wave to have a node at each end, KL must equal n pi. N can take any positive integer value, each representing an allowed wavelength. N between 1 and 4 is shown here on the left. As you can see, that all that n represents is just how many half wavelengths we've squashed between these boundaries, and each increase in n by a value of 1 means an extra half wavelength is fitted between these boundaries. The frequency and the speed of the wavelengths are also constricted to certain values. These in turn depend on tension, mass density of the string, and the n value of the particular wave.